was just here mere days ago, graduate students in the same place. Kaitlin came to us from Columbia, Barnard, and stayed here for the proper amount of time, and then went off to Harvard. And in the meantime, she did all sorts of fun things having to do with stuff that she will be talking about today. Although that in the background looks like something from the system. Kaitlin was one of those fun graduate students to have around from a number of standpoints. Scientifically, she was very interested in organizing things like order of magnitude discussions and even a star formation workshop that had 2 instances, which stopped happening once she left. Today she's going to tell us about things she's been doing in the meantime, between then and now, as a Harvard CFA fellow, and now a that's right, ITC and now as a Hubble fellow going to Cullen. So take it away.
All right. Well, thank you guys for that introduction, and thanks for showing up during the summer. I guess there's AC in here, so maybe it's not that impressive that you're here. So I see a few familiar faces and a lot of unfamiliar faces, so I'm guessing there's a large fraction of new graduate students in the room. Anyway, so I'm going to talk about work that I did not do the project. I turn over everyone just to so as I promised Chris, I won't talk about work from my thesis, although that is what the picture is in the background. So even though I'm not talking about my thesis work, I am of course still going to talk about binaries. And I will start off by trying to convince you that binaries are by far the most important thing in all of astrophysics. I know I stand in CITA, and I'm still going to say that. And I hope by the end of my talk you'll be convinced. After that, I'm going to talk about triple systems, so both stellar and planetary systems. And I'm going to talk not about how we form these systems, but about some interesting dynamical instabilities that can arise once these systems evolve. At the end of my talk, I'll also spend a little bit of time talking about circumbinary systems, which I think are pretty cool too. So, why are binaries the most important thing in all of astrophysics? So, I have several pictures up here. They're all labeled, so you don't have to guess what they are. But what I'm trying to represent here is the wide array of astrophysical effects that we need binaries to understand. So of course we have, this is a plot of the Hulse-Taylor binary. So this is a pulsar binary system. This is the decay rate of the orbital period as a function of time. Blue is the theoretical prediction, red is the data point. They match well. So we need binaries to confirm GR. Of course, this is an image of a type 1a supernova, which tells us about dark energy. So, although the models for the production mechanism for type 1a supernova remain uncertain, both the leading contenders involve binaries. We can confirm the existence of stellar mass black holes only by the existence of binaries. This is Cygnus X1. You can see the emission coming from right around the black hole. This is in X-ray, I think. Of course, people here at CITA are very involved in detecting gravitational wave signals, so you all know that one of the dominant sources for the actual direct detection of gravitational waves comes from binaries. For any of the planet people in the room, you actually desperately need binaries to characterize extrasolar planets. And the reason for this is that the only way we can do a very good job of characterizing the properties of stars is from the very special type of binary, spectroscopic eclipsing binaries. Because these systems tell us about the relationship between mass, luminosity, spectra. So if you want to understand your exoplanet, you need to understand your star. And if you want to understand your star, you need to have some that are in binaries. And finally, since I'm at CITA, I will mention how binaries may also be involved in reionization. I'll just point out to any of the graduate students in the room, if you haven't picked your thesis project, there have been, in fact, at least 2 Nobel Prizes awarded for work that's related to binaries. You could count the Giacconi's binary as a Nobel Prize because that was for X-rays, which also came from binaries. So if you haven't picked a thesis project, make sure you include binaries. So, why should the cosmologists in the room care about binaries as well? So I'm going to talk about a paper that Charlie Conroy and I wrote. It's just been accepted, actually, about why you need binaries to reionize the universe. So These are O stars that are running away. They are moving at high velocities, maybe 30, 40, 50, 60 kilometers per second. And they are different from almost all of the other O stars that we observe in our local galaxy in that they are single. So they're not in binaries. And there's two different production mechanisms we think we need to make runaway O stars. And both of them require binaries. You can either imagine that you started out with a binary, one of the stars evolved, went through a supernova, exploded, and ejected the companion. Or you might imagine that these arise from dynamical interactions in dense clusters. So you have a binary interacting with a single star, they do a little dance, one of them jumps away, and that becomes your runaway O star. So why should you care about these if you're cosmologists? Well, if you have binaries and you have O stars, you might expect to get runaway O stars at any point in the history of the universe. And we know that in order to produce the number of ionizing photons we think we need to reionize the redshifts from, say, 6 to 12, you can't just do it with AGN, you need to include the luminosity of O stars. But galaxies are really dense, and they do a really good job of absorbing ionizing photons. But there's a catch. At high redshift, we think that galaxies are much smaller. So if you make your galaxy small, and then you have O stars and binaries that dance around and kick each other out, they travel a significant fraction of the distance out of the galaxy during their short but important lifetimes. And so because the galaxies at high redshift are so much smaller, these O stars can escape to the outer portions of galaxies and therefore contribute a much higher fraction of their ionizing photons towards the process of reionization. So what I'm showing here is some models that as a function of halo mass, this is both the escape fraction of ionizing photons or the enhancement of the escape fraction. This is sort of a more robust number, so this number is a little bit more uncertain. And what you can see is that if you look at the escape fraction from non-runaways, it's very, very small, again, because all the photons are being absorbed. But the escape fraction from runaways, especially in the lower halo mass galaxies, can be quite high near unity. And so at this sort of peak between halo masses of 10 to the 8, 10 to the 9 solar masses, you can get enhancement factors in the ionization fraction up to a factor of 10. So for the cosmologists in the room, this is it for the talk. No more cosmology, but you still need to think about binaries.
But what's the typical velocity of this runaway?
So 30, 40, 50 kilometers a second. So they can travel, many parsecs in there.
I guess the thought whether they can escape the galaxy or not depends from where they are ejected in the galaxy.
Where they are.
Where they are ejected in the galaxy.
Yeah, so sure, the ones that are ejected in the center, in the dead center, don't get that far out. But so this is including, this is for a stellar density profile that just traces the gas density profile. You get slightly different answers if you change the distribution of stars. But this is including stars, sort of the cumulative effect of stars distributed throughout the galaxy. And if you put things in the disk, you get a higher escape fraction because then you can escape more in two directions than in one. But sure, it also depends on halo mass, and it depends on your galaxy model, and it only works if you really believe that high redshift galaxies are small. If they were, the same size as the Milky Way, it would be a pretty small effect. Okay, so goodbye to cosmology. I'm sorry. I'm going to go back to binaries, and in fact, I'm going to go to talk about triples, because if binaries are cool, clearly triples must be even better. So binaries make up an enormous fraction of all of the stars we see in the sky, as much as 100% if you're talking about O stars, maybe 50% for G stars. But triple systems are no small fraction, so maybe 15%, although the true fraction is very uncertain. It's difficult to get a robust statistical sample, but they're not rare. And these may be very crucial to the formation of close binaries through dynamical interactions. And we observe that even at the earliest times, even in pre-main sequence groups, the multiplicity fraction is very, very high. There are many triples, quadruples, quintuplets. So they're not a small contribution to the total stellar population. And so what I want to talk about is what happens as these triple systems evolve. And before I do that, I just want to remind you of some basics of Astro 101, and that is that as stars age, they move off the main sequence, and they follow up on the red giant branch, and finally they end up all the way on the AGB branch. And when stars are undergoing on the asymptotic giant branch, they are both very, very puffy. They can be as big as an AU in size, and they lose mass at a relatively rapid rate. So just keep those two facts in mind. They will become important and obvious in one moment. So, since I'm talking about triple systems, you might think we want to consider stability. So what do you need to do to make a system of 3 gravitating bodies stable? Maybe not surprisingly, you need the configuration to be very hierarchical, like this set of blue circles over here. So you have one system that's in a relatively close binary, and then the third object is separated wildly. And if you have a system that looks like this, you can be stable for the lifetime of the universe, and it's not very interesting. On the other hand, if you have a system that looks like this, where A in, so the separation between the inner binary is not much smaller than the separation of the outer binary, this will become unstable very, very rapidly. And the ratio between these two at which instability sets in is something like a factor of 3, although it depends on the mass ratios and the eccentricities involved. So, if you remember what I just told you about what we all know about stellar evolution, we can consider a nice, stable, hierarchical triple system like this in a lovely cartoon and then ask what happens as the primary star evolves and starts to lose mass. Well, the orbits are going to change. So it's going to blow up, it's going to lose some mass, and the orbits are going to expand because, of course, the gravitational potential has changed as the primary has lost mass. But the two orbital separations are not going to expand at the same rate because the total enclosed mass of the inner system has changed much more than the total enclosed mass in the outer system. And so what we can have happen is a system that can start out its life in this nice hierarchical stable situation, transition to an unstable situation like this. So if you do that, this is what happens. So this is a movie where this blue star is now a white dwarf. So he's lost all of his mass on the HV phase, and now you can see that you get lots of exciting encounters. Remember what I also said, that during the HV phase, this star can be an AU in size. So while you're undergoing all of these close encounters, you have a very, very high probability of having a collision. You're probably not listening anymore at this point, just watching these evolve. But in case you are, the sort of punchline is that when you play this game, any interaction that you might want to have between stars in something like a globular cluster, where you have very, very high densities, and therefore a high probability of having a random scattering event, you can do this in the field as long as you start out with a triple system.
Well, I would say you should start out with the right triple system.
You have to start out with the right triple system.
That's the possibility of things that you say.
Yeah, so it turns out, and I don't know if I have this plug in here, it turns out that if you take the observed population of triple systems, which is not necessarily the best representative sample, and then you evolve the primary and ask whether or not the system becomes unstable, and then multiply that by the fraction of systems that undergo collision, you end up with 30 times more physical stellar collisions from this mechanism than from anything else you can do in a globular cluster. It's still a very small rate, something like 10 to the -4 per galaxy or per Milky Way type galaxy per year.
I would say what percentage triples will undergo anything interesting?
It's something like 1% or less of triples actually go unstable. So it's a small fraction of triples. Sure, that's correct. At least a small fraction of the observed triples. So that finally finished. So we can look at this a bit more quantitatively. So this is a plot of the evolution as a function of time. This is sort of the exciting part where most of the mass is being lost. This is separation in AU. The different colors are the different pairs. So red is the mass-losing star and the inner component. Green is the mass-losing star and the outer component, and blue is the other two. What you can see is that as the black dashed line goes down, which is the mass loss on the other side of the y-axis, that the orbits slowly start to expand. They hit this critical point and go unstable. And then you can see this blue dashed line here. This is actually the physical radius of M1, the HV star. And you can see in this particular case, the orbits cause the two stars to plunge into one another repeatedly. Now in this case, we didn't stop the calculation at this point. This is just a straightforward three-body integration, so there's no tidal effects or anything like that. But you can see that collisions are possible. Ignoring the effects of the collision, in this case, one of the stars is ejected, just like you saw in the movie, and you end up with an eccentric, reasonably close binary. So you can basically, as I said, get any sort of chaotic orbital output that you would get in a globular cluster, and then you get more encounters from this mechanism than from all the ones you would get in globular clusters combined. Just to show again what the close approach statistics look like. So this is the stellar radius and the closest approach. And this is the fraction of stars that undergo a close approach at this distance. You can see that there are many close approaches at about 1 AU, which is where the star's outer envelope is.
Sorry, what was the last one?
The blue line is the stellar is the closest approach, and the blue line is the stellar radius at closest approach, and the red line is the two stars closest approaches. So that there's a peak here because this is the stellar radius when the instability sets in, and the red line shows the number of systems that cross through that radius at the interesting time. So you get a few percent of systems that undergo a close
So
approach.
another way to get the star big is actually being a much closer binary and do mass transfer. As long as it's more or less conservative, that increases the size of the orbit a lot too.
That's right. So when we calculated the numbers of these systems, we ran the observed triple sample through Hurley's binary stellar evolution code. So most of the time when you get mass transfer, you actually get the orbits coming together in many cases, and so that doesn't trigger an instability. So the systems that are most likely to undergo instability are ones that never have mass transfer.
I think that may depend on what kind of stars you make. For more massive stars, mass transfer is more often stable because it's slower.
Sure. So this is only for stars that don't go supernova.
Yeah.
You can certainly get the same thing with the supernova, but then you can't
No,
do
that
it
too.
adiabatically.
Yeah, no, but I really meant it for it's thermal timescale mass transfer. You have a much bigger chance of still expanding the orbit. Anyway, it's another way to. You basically all you want to do is make your inner orbit wide. Right?
Exactly. You want to make your inner orbit wider while not making the outer orbit wider.
If you mass transfer and expanding the orbit, it's not very long most other
Well, you can increase your separation by a large factor.
the independence is relatively less important.
I don't know.
So the third companion is also less important?
What is the really rational? There are a lot of other effects, like conflict.
Sure. So
Anyway, so
I don't think
it
I
should
have
work.
any-
I guess
yeah,
that's
no.
really the main.
it should, yeah, I think it probably is, it's certainly easier to calculate the statistics for the non-interacting systems. That's certainly the case. And we haven't included tidal effects, but I don't have this plot in here, but the reason that I think that's probably okay is that when you look at the close approach statistics, you typically get very large jumps between one close approach and the next, so that you don't have multiple close approaches at 2, 3, 4 tidal radii. So that probably you either aren't interacting tidally or you have a tidal interaction and then we stop the calculation at that point.
This, I don't understand, it's a thing, and body simulation.
So this is from our, well, the radius is from a stellar evolution code, and the dynamics is from an embodied calculation.
So the initial conditions are generated by the evolution.
Right. So we take both an observed sample of triple systems, evolve them. We evolve them to see if they go unstable using a coupled binary stellar evolution code, and then just evolving the orbit of the third one, assuming that the inner two is like a single star. And then to get the statistics of what happens once the system goes unstable, that we derive from actual n-body calculations. And those we include, so we include the mass loss in the n-body calculation. Does that answer your question?
Yeah.
Okay.
When you were drawing a distinction between the observed population of triples and maybe what the actual, how is that defined?
I don't think we know. I mean, you can only observe, you only find triple systems when, either one of the components is pretty close, because then you either get it through spectroscopy or high resolution imaging, and then it's easier to find the third companion if it's relatively far away. But if all the orbits are widely spaced, then it's going to be very hard to find those systems. And since what matters most for the instability is the ratio of separations, you might be missing a bunch of systems. Although, if you increase the physical separation and hold the ratio fixed, you'll also get fewer close approaches, because the close approach depends on the initial separation. So maybe it's not all the interesting ones. I should say we make a synthetic sample of triples as well, which is just basically making two sets of binaries. So you take the binary statistics, which are all well known, and then you add a third star, assuming that those statistics look just like binaries, and you get the same answer, which is, you can decide if you think that's convincing or not. Okay, so I said that you could do all sorts of fun things that you could normally only do in globular clusters, so I just want to give you one example of something that you might be able to do with this instability, and that's make a system that looks like Sirius. So even theorists like me know which star Sirius is in the sky, I hope. But if you don't know what it looks like, it's actually a binary, so the star you see is Sirius A, a 2 solar mass main sequence star, and Sirius B is its about 1 solar mass white dwarf companion, which means that we think the progenitor of Sirius B before it lost mass was about 5 solar masses. And this system is a little bit funky from a stellar evolution perspective because it has a semi-major axis of 20 AU and an eccentricity of 0.6, which is really high. And if you rewind the system back in time to when the primary was more massive, the orbits come together, and then you would have expected it to undergo mass transfer and some sort of common envelope evolution and probably end up on a much more circular orbit. So if instead of telling your standard stellar evolution story, you instead imagine that Sirius started out as a triple system, it's actually much, much easier to explain its current orbit. So what I'm showing here is a series of n-body runs that we did where we tried to see if, just qualitatively, we could reproduce something that looks like Sirius. So we start out with 2 components in a triple that look like the 2 stars that are currently in the Sirius system, and then we add in a third component that is of similar mass. We consider a range of masses, which I'm not showing on here. They're all about a solar mass. And then we start out the systems so that they will go unstable with the inner semi-major axis here around several tens of AU, the outer one around several hundreds of AU, and then we let them evolve. And you can see that we get a few different populations. We get a population out here where you eject one component, and then you end up with a wide eccentric binary. You get a few systems that sort of get marginally destabilized and don't do a whole lot. And then you get this population of close orbits, so tens of AU, and very highly eccentric binaries left behind. And you can see this red dot here, that's right where Sirius is. Now, if you wanted to be...
So
the third object was ejected in all of these systems, that's right. You might even say something like, oh, since we've neglected tidal effects, maybe you expect the real system to mostly end up at slightly lower eccentricity than these guys up here. So this isn't a statistical demonstration that this is the most likely way to form Sirius A and B, just a suggestion that perhaps it had a more violent history. So stars are cool, but planets are equally cool, if not cooler. So if you can play this same game with 3 stars, you can actually play it even better if you take 2 stars and 1 planet. And the reason for that is what this instability relies on is the fact that the orbits expand at different rates. So if you put a planet around one of the stars instead of another star, then the differential mass loss is huge between the inner system, which is star-planet, and the outer system, which is star-star. And so what I'm showing here is, again, as a function of time, this is where all the mass loss is happening. This is for an A star. The ratio of the planetary separation to the stellar separation, and you can see that these increase drastically, almost by a factor of 2. So what that means is, as Yan-Chin pointed out, in the stellar case, it's kind of hard to construct a lot of triples that might be in this special configuration where they evolve to become unstable, but it's perhaps much, much easier to do the same thing with planets. And that's because you can just have the planet start out much closer to the star initially. Now, you might ask, well, are there planets in binary systems? Perhaps surprisingly to all the theorists, the answer is yes. So this is a plot from exoplanets.org. This is orbital period and the M sin I of the planet. All of the red dots show you planets in binary systems. It's very hard to constrain anything about the population of planets in binary systems. The main reason for that is because people don't really look at binaries because everyone thought they wouldn't be there. And so the fact that we found this many, while we were trying very hard to look at anything but binary systems, suggests that their rates may in fact be similar to those around single stars. So if we trust the Kepler sample, there's a whole host of planets around binary systems. I'll also point out that the systems that we're going to be talking about where you can get this effect that means the planet is, well, if the binary is separated by about 100 AU, you want the planet to be sitting at 10 AU, and that happens to be where the peak of the binary separation distribution is. So we could be talking about a whole load of systems in here. So if I play the same game with test particles or planets around binary, which is what you're seeing here, now you can see that as this blue guy is starting to lose mass, the orbits are getting perturbed, and they're starting to bounce around. I should point out that Yan Shin and a former graduate student, Alex Mudrick, have done some great analytical and numerical work looking at this without mass loss, just the outcome of planets around one of the star in a binary system, and all of our results would do very well with theirs, although what we're doing here is just the transition between the two stages. So you can see you get the same kind of interaction now, except the planets, instead of actually perturbing the orbit of the stellar system significantly, they are changing partners and bouncing back and forth between them. Of course, this star is still probably on the AGB, in the AGB phase here, so you have the chance for collisions. The star can penetrate the envelope of the AGB, maybe eject it. So you can have a lot of exciting things going on. Go ahead.
Sorry, because maybe somewhat too general, but I mean, as this star is slowly evolving, if you have this ratio of, I guess basically if you have a ratio of orbital separation that's already not that large, at least in many cases you get quasi cycles and you would evolve. So are you basically assuming that they're somewhat coplanar, so that that's not a problem?
This is the coplanar circular restricted three-body problem right now. So we did do some moderate inclination runs where you don't get cosi because the inclination isn't high enough. Certainly, if you got cosi and then you drive the inner orbit in and you get tidal damping, it probably won't work. I think that's true. So this leads in nicely to this slide. So what I think is really cool about this problem is it's a tiny perturbation on the circular restricted three-body problem, which still manages to be complicated. But it's great because you can write down the equation of motion in dimensionless coordinates. And the really cool thing is that you have a conserved quantity, you have the Jacobi constant. And what the Jacobi constant does is it tells you for a given configuration where you expect the planet to be able to move under the influence of these two rotating gravitating bodies. So in this case, you can see that for this value of the Jacobi constant, this planet is allowed to bounce anywhere between these two stars, but he can't escape. And so we can watch that same movie, but now do it in the rotating reference frame, and I'm going to plot the Jacobi constants for all of the planets. Now, you can see that constant's sort of a funny word, because obviously these are changing. But they're changing slowly as the star loses mass. And so now we can actually really understand what's going on. So as these curves open up here at the first Lagrange point, this bottleneck becomes wide enough that the planets can start bouncing back and forth. And then you can see that their orbits are still, as you would expect, constrained to lie within their Jacobi constant. But because the planets are evolving chaotically, as the star continues to lose mass, you can get small changes in the Jacobi constant from one particle to the next. So you can see as they're evolving now, here's the cool part. As mass loss continues, the Jacobi constant starts to make that curve inch off. And so now the planets are actually getting caught around the secondary star in the system. They've been lost from the mass-losing star, maybe saved in the event that the mass loss might have interfered with the lovely life that was sitting on that planet. And now they're caught around the secondary in eccentric but orbits that we integrate out for 100 million years and remain stable. So you can just see this in a few snapshots. This is the initial condition. You can see the curves open up, it bounces, and at the end, once the mass loss is finished, you end up trapped around the secondary. I should point out this is similar to a mechanism that was described by Heppenheimer and Poco in the 70s, but in that case, they were considering a planetary-like system where they were asking how you get irregular satellites around Jupiter in our own solar system. And it's the same story, except in that case, you want to think about, instead of the star losing mass, you think about Jupiter gaining mass. And so that still shifts the mass ratio, which can change the Jacobi constant.
Is there a reason that they all switch stars?
I only plotted ones that switched stars. The majority of the test particles in those runs collide with one of the two stars. We never see one end up caught around the primary. So you can see this again quantitatively here. This is time, the exciting mass moving part. The black curve here is the stellar separation. The colored lines are planetary separations. This is the instability boundary. You can see here they jump across, they start bouncing back and forth. And then this gray line is the new stability boundary around the secondary. You can see that we get a whole host of systems on eccentric orbits that still hug the instability boundary of the secondary star. This is the same plot, but now I'm just showing the Jacobi constant. So you can see they change while mass is lost, and then as you would expect, once the mass loss stops, the Jacobi constant once again becomes constant. So there's a few cool outcomes that you might expect if this mechanism operates. You might expect to find wide, so planets around tens of AU, planets around main sequence stars in a white dwarf main sequence binary. So that means the white dwarf loses the planet and it goes and lives around the main sequence star. You might also expect to find, if you're lucky, planets around the tidal radius of the white dwarf. And this is because, just like the stellar disk, you get lots of close encounters. If you get enough of these at not too close to be disrupted by the star, but a few tidal radii, you might be able to capture them into close orbits. And if you're really lucky, you might be able to find planets around the older white dwarf in a white dwarf binary system. So you start out with two main sequence stars, one evolves, you lose the planets, they go to the other one, and that evolves, and they come back home where they started out. One interesting fact about white dwarfs is that their habitable zone coincides with the tidal radius. So if you tidally capture them, they would be in the habitable zone. Now, it seems like a pretty dramatic evolution to keep life, but bacteria are creative. And multi-planet systems are probably destabilized even more. So, triple systems are cool, planet systems are cool, and I think circumbinary planetary systems are maybe the coolest of all. So these are three systems that have been found by the Kepler satellite, Kepler 34, 35, and 16, and these are all close eclipsing binaries that have a planet near the boundary of the orbital stability in the same plane as the binary. That's what these diagrams are showing here. These are all have mutual inclinations that are smaller than our own solar system. They have slightly different numerical set of stability constraints than the type of planetary systems I was just talking about, but not so different. They have to be hierarchical. So what I want to talk about specifically is not circumbinary systems in general, but the most famous circumbinary system that we've all heard of, even if we don't know it. So you might have thought that it was sad, Pluto is not a planet, boo-hoo. It's okay, Pluto is much cooler because it's in a circumbinary planetary system analog. So Pluto has a moon, Charon, which has a mass ratio of 10 to 1. So dynamically speaking, this is not a moon. Our moon is big and that's a mass ratio of like 100 to 1. So this is definitely a binary. And you may also have known that Pluto and Charon have these two well-known actual satellites with mass ratios of 10 to minus 5 at most, called Nix and Hydra. So now we have a circumbinary multi-planet system. And what's even cooler is that about a year ago now, they found yet another moon orbiting in between Nix and Hydra. So now we have this really cool, dynamically packed circumbinary system. And it's pretty hard to think of anything that is more exciting from a dynamical perspective than a system that's as complicated as this. As much as I like the circular restricted three-body problem, now you're done. There's no way you can describe this well in terms of the circular restricted three-body problem. So I'll just point out one other thing about the comparison between the Pluto-Charon system and one of the Kepler systems, and that's, if you come down here, you can see that we've got all of these nice parameters about the system, but if you look at the masses of Nix and Hydra, which are the only ones that are known, we don't know the mass of this new moon P4 orbiting in between them, you can see that the error bars on the masses are really, really big. They're at least an order of magnitude. Whereas if we look at this Kepler system, and we find the mass of the planet, you can see the mass is known to two significant, to less than a 0.01, or slightly more than 0.01 Jupiter masses. So I think this really speaks to the power of real binary stars in Kepler. That's really the reason that we can get these masses so precisely from timing solution and radius measurements. Whereas for the Pluto-Charon system, right, these are rocks. This is the problem with rocks. They just reflect light from the sun, and so it's really hard to do things like measure masses. You have to make all sorts of assumptions. But what I said before is that the system is dynamically packed. What that means is that its stability is very, very sensitive to things like changes in mass. So what we can do is place much tighter constraints on the masses of these two things just by knowing that there's another third body in the system. So I'll just remind you, in case you're unfamiliar with what albedos mean, because they're going to be important in a little bit. We have many examples of a wide range of albedos. So this is the amount of reflected light that an object gives off. So asphalt has a very low albedo. Pluto and Charon have sort of intermediate albedos. Enceladus has an albedo of 0.9. That's one of the highest in the solar system. Snow outside of Toronto has high albedos. Here it's probably more like soil. So you can see there's quite a range. So what we do is now take this system with this new satellite, say, okay, we know it has some range of orbital periods, and then we ask, for what masses of the other two satellites, Nix and Hydra, does the system remain stable for the lifetime of the solar system? And so what I'm showing here is some diagrams that show, the color shows you how long it takes for the object to get kicked out as a function of its semi-major axis and eccentricity. And what I just want to point out to you is that when you just populate the system with relatively dynamically cold, so low inclination, low eccentricity, possible orbits for this new guy, as you march down, as you march up in albedo in this direction or down in mass, you get these interesting features appear, and I'll show these in a little bit more detail later, but you can see there's a lot of structure here. But if you look at the numbers up here at the top, the lifetime for the new guy is very, very short compared to the lifetime of the solar system for masses that are anywhere near what previous studies had suggested. I'll just point out that if you're going to look at orbits around a binary system, you have to be a little bit careful. So if you're going to do this, just keep in mind the fact that if you try to put a test particle in orbit around a binary, it's no longer going to be a Keplerian orbit in many circumstances. And so what you can see, this is just a demonstration of that here. So I'm showing the orbits for a bunch of these test particles as a function of time. This is the physical separation over the semi-major axis. So this is just physical separation. You can see they're pretty flat. These look like they're circular. But if instead I ask you what is the Keplerian semi-major axis or the Keplerian eccentricity over the orbits, you can see it varies widely. So if you just place a particle on a Keplerian orbit about a binary, you don't necessarily get a cold orbit. So you have to play a sort of special game to come up with the most circular orbits, but you can do that. And so we can look at the stability under these two assumptions. So what I'm showing you now is as a function of the mass of the two satellites, the time at which the particle, the new moon, gets ejected, so the crossing time, the time at which the orbits cross. And what you can see is that as I decrease the mass, the crossing time increases, and although it's very expensive to run calculations all the way out to the lifetime of the solar system, gigayears, you can see that they all fall on these very, very nice power laws, and we can extrapolate up and find that for the lifetime of the solar system, Nix and Hydra have to be very, very high albedo, maybe as high as 0.5 or 0.6. This is if we play the same game, but I did this careful calculation where we now ask that the satellite is on the most circular orbits. You can see now we have a bit less restricted constraints on the albedo, so 0.3. But this, even in this case, we now have an order of magnitude reduction in the masses of Nix and Hydra. I'll point out some other cool features that we find in these NY simulations. Just like those contour plots I showed you earlier, there's a lot of structure in the crossing time. So this is the period of this new satellite in terms of Pluto-Charon periods. This is crossing time again. The colors show you different mass cases. And what you see here is there's this big hole right at the 5-to-1 resonance. So we find that, maybe not surprisingly, the resonance is very, very destabilizing. And I'll point out that the other two satellites, Nix and Hydra, are also very close to, but not in resonance. This is something that's been seen in the Kepler multi-planet system. So perhaps we're seeing some sort of resonance overlap destabilization in this region that's making it easier for the objects to survive outside of resonance. It's also not a function of Pluto's sharing eccentricity, so I'm going to skip that and just say that the reason that this is exciting, aside from the dynamics of it, is that we can also comment on the formation of the system by better constraining the albedos. So one of the dominant, most prominent formation models for the Pluto sharing system is that you have two partially differentiated bodies crash into one another, and that forms initially just Pluto and Charon, and then a debris disk of other material, mostly coming sort of from the surface of those two bodies. And the reason this is important, it's a little hard to see on the screen, but the red shows you composition here. And if you look, you can see that all the stuff that goes into this disky material out here outside of Pluto Charon is bluer, meaning it's icier. And so this might be very consistent with what our numerical integrations have shown, which is that the albedos of the other satellites have to be high, which means they have to be more ice-rich than the partially differentiated bodies that went into forming Pluto and Charon. So there's still a lot more work to be done on the details of this, but so far the picture looks roughly consistent. So I'll just finish up, and I hope I've convinced you that binaries are the coolest thing in all of astrophysics. And I just remind you that we talked about a couple different types of dynamical instabilities, primarily ones that are induced by stellar evolution-driven mass loss. They can produce all sorts of exotic, compact binary systems outside the field. So if you want to make field compact binaries, it's a great way to do it. And we can also play the same game in planetary systems. And finally, I've talked about how we can have solar system objects serve as great probes of circumbinary planetary dynamics. And I will stop there before 3 o'clock. Oh, okay, I'm going to ask about Pluto and Charon.
Well, I think that problem is really rather complicated because the third body can have mass, and ends up in the 3 body doesn't stabilize everything else.
Right.
That's what we call everywhere in the 3 body, all kinds of mass.
Yeah, so we have only done the 2 massive satellites, well, or the third if you consider Charon. I think the reason we didn't do it in this case is because the orbit of people are so poorly constrained right now that it's difficult to cover the full parameter space with actual massive bodies.
Well, and also is that if you use those more reasonable orbits, you want to get at either cluster,
So if you only use the what?
If you use more reasonable orbits.
Yeah, so if you use the cold orbits, it's you still reduce the masses based on the previous astrometric fits by a significant factor, but it is better.
Yeah. It's hard. I'll argue that the real approach to is one of the instances is external orbit that didn't happen.
Okay.
So that would be your depends on your assumption that it's just one.
Exactly.
Which is probably pretty high.
It could be. So we just fix the density and then just sort of calculate.
So we don't understand.
The density,
We only was
physically, I think the density can't be less than that. That's too, like other numbers. So you have
Yeah, it's a really
30%, maybe 22, but not on those.
Can I ask a question? So going back to the circumbinary planets, given what we know about the circumbinary planets now, what fraction of AGB stars are going to have penetrating electrons from the planets that are just stabilized?
Circumbinary or planets around one star, around the AGB star?
I don't care where they come from, but they have to get into the AGB star envelope.
Yeah, so these guys, these guys are all on small enough orbits that they certainly encounter the envelope. You can see the scale here. So, this one certainly will. I'm not sure about this two. Because well, more importantly, these aren't definitely stars. These are massive. So they do lose mass. They do have bigger ones. So actually I don't know the answer for these systems in particular. And we don't have any observations of planets around stars greater than 2 solar masses. So I don't want to disagree with me on that statement. Okay, I'm going to say that that's true for now. So it's hard to know what that looks like.
Are you long 2 solar masses? And 1
Well,
solar mass star becomes an AGC.
Well, it doesn't get very big, though. It doesn't move very
Oh.
fast.
No, 1 solar mass star uses 0.4 solar masses. No, nothing. But these ones are too close. I agree. They interact differently,
Yeah.
and then something will happen already.
All right, let's thank Kaitlin and